ZKP accelerations. And today I will share like some recent progress of our development, our recent findings, and our next step in the future. Especially, I want to share with you about like something that you can expect in the next year, like what kind of hardware you can see on the market. So some background about ZK Snark. Honestly, I think like we can skip this part because today everyone is so professional. So in short, it's a short proof about some statement is true. Usually it's about some computation is correct. And the proof itself should be short and it should be fast to be verified. And ZK Snark is like something like you can hide the information behind the computation. And it has several nice properties to make it useful. For example, it can have some concept of verified computation. You can ensure the desired computation is faithfully evaluated. You can hide the knowledge about a specific piece of information. Sometimes it is useful, for example, Zcash, and the size and the proof time should be short. And one example of the application is like a ZK rollup. And the basic idea is like you have a bunch of huge amount of computation which is already happening on the layer 1. It's about to verify some computation is correctly evaluated. And by moving it out of the first layer, you can reduce the computation on layer 1. The problem is like, how can you trust the result is correct? You have multiple methods, but the ZK rollup basically says like, using some cryptographic method, you can spend a little computation to ensure that the whole bunch of computation is correctly evaluated. And that's why there's so many projects using ZKP. Some of them are L2 projects, and some of them are L1. And in general, like the system behind the ZK Snark consists of 3 stages. The first stage is you write your applications using some DLCL, and then it was transformed to some kind of Snark-friendly format. And finally, the encoding, such as R1CS format, is sent to a Snark backend prover. And in the last step, you have a huge amount of computation. That computation is so expensive. Of course, it's already much better than 20 years ago, maybe 10 years ago. But like, it's still so expensive that restrict its application. At least restrict the size of the circuit you can write. And that an example is you can see the Alio have at least like 300,000 RTX 3080 equivalent GPU running on their test late 3. How about the future? You have more ZK related project, and each project are using larger and larger circuit. You need a huge amount of computation power to support the provers. And then we ask how about the specialized hardware? It can immediately bring you several advantages. For example, you can have short proof time, or equivalently with the same time budget, you can work with a much larger circuit. And you can spend less money compared to GPU, like performance per dollar, and you may have less electricity bills. So if we look at the ZK hardware acceleration, what kind of problems we have to look at? So today I will discuss 3 points. The first is like which part of the system, which part of the computation should we accelerate? And then the second is recent finding about the diminishing return after we accelerate the MSM and NTT part. And the last part is like how can we handle the diverse kernels in the long tail distribution. So the first part, let's look at the general ZKP proof process. Although like this summarization is pretty bad, but like sorry for that. So in general, you first write out your witness, and then you commit the witness. When you commit the witness, you see it as a polynomial, and then you perform some kind of polynomial commitment, and finally you prove that the witness is correct. And if you look at the strip the mathematical way, and if you look at the computation only, you will find like they involve like large field arithmetic, for example, 256-bit additions, multiplications. I mean modular addition and modular multiplications. And then when you commit your witness, you have some kind of multi-scalar multiplications and numeric theoretic transform. So we start with MSM and NTT. The reason is like first, those two are the most time-consuming part. Before acceleration, it takes like 80% of your execution time in some cases. And the second thing is like they are loosely coupled with the CPU thread. So that means like if you offload them into a specialized hardware, it will be pretty easy because the offload overhead is small. Just imagine if you want to use the accelerator for every single modular multiplication, then the system overhead will be unacceptable. So that's why we started with the first two. And in the past year, we developed several systems for these two, actually three kernels. For the MSM, the implementation is some kind of similar to the software implementation, which is the bucket method. You divide the scalar part into multiple short bit number, and then you use a bucket to accumulate them. And the hardware design consists of multiple independent process elements. Each of them have a standalone ALU which can perform full EC point add and double in a pipeline fashion. So each cycle it can finish one Z operations, and you have all the control logic. The tricky part in this design is because this is a pipeline design. You have a huge number of like EC group add and operation on the fly, and they might be added to the same position of the table, and you need to carefully handle those kind of potential like write conflict problem. And on top of the PE, you have multiple PE located in one FPGA board, and each FPGA and multiple FPGA die are located in one PCB board. And that forms our final system. And we reduce the MSM on BN 254 curve the execution time of like 1 billion point evaluation, like it was reduced to below 200 microseconds. If you're familiar with, if you have a sense of like what the expected time if you run this on CPU, you will know like how much difference it is. And we also have some kind of NTT implementation. The general implementation follows like a kind of 4-pass algorithm. And like I would assume like this is like a common way to do NTT. You organize it in a matrix, and then you do NTT row by row, and then column by column. And this is also how we do it on hardware. Some new problem emerge when we do it on hardware. The first is like the memory access pattern is pretty bad, especially if you have a lot of data on CPU side. Sometimes we see some older design, hardware design that like require the CPU to do some kind of tricky data reorganization to permute the data in the NTT array. And because that part was happening on CPU, that makes the CPU overhead pretty big. And we have customized the intermediate data layout to make every memory access, no matter on CPU, on chip, or on our accelerator card, to be much more hardware friendly. The second part is like you usually have to store a huge tweet factor array, which is near the size of the entity vector itself. On CPU, it's good because like CPU have a huge memory, but like on your FPGA, the memory is pretty restricted. So you may come up with some method to compute on the fly, but to compute on the fly, you have to double the computation. That's also bad. So like we use some kind of a mixed storing and compute strategy to not only reduce the memory footprint but also minimize, which means like the compute on the fly overhead is near zero. So that is some kind of good thing. And with those designs, we have a massively connected FPGA system. Well, the hardware design is kind of boring here. But in general, we have a performance like this. Okay, so if you have like a 1 billion point entity, you can finish it in like 200 and about 200 microseconds. So the speed up comparing to CPU over here is like smaller than the MSM because entity itself, the computation is less than the CPU. So the transmission time becomes a more important problem. And finally, we have like kind of Poseidon macro tree, in which case the keyboard is a keyboard problem. Yeah, so like 1 billion import. Like I remember, I think the design is about 64-bit Goldilocks if my memory is correct. So it can finish in 43 seconds. So this one is basically PCIe bounded. And so all the performance we show here is not a single FPGA die. It can actually come from our FPGA server. So it can have multiple accelerator card. Each card have several like process elements on it, and this is how it looks like. A huge machine with like customized high bandwidth interconnect, customized PCB design, and customized power delivery and water cooling. And the problem is this is too big, too heavy. So that's why we are developing ASIC design on top of our implementation of like the FPGA design. Because FPGA itself on hardware, it's not so efficient because like to make the hardware reprogrammable, you lost so much thing. For example, your frequency is restricted to 300 megabytes, that kind of stuff. So what we are going to do in the next step is to squeeze all the performance, all the computation power in that machine into a single accelerator die. And that's our project. But like this is not the end of the story because we found something bad after we accelerated the MSM and NTT part. For example, if you accelerate your circuit itself is kind of a Poseidon hash circuit, and if you look at the performance before and after acceleration, you will see that like before acceleration it takes 800 seconds, and then after acceleration you have 5 times speed up. But after acceleration, MSM entity itself added together contribute only 4% of execution time. To make it more clear, you can see this figure. So the orange part is the MSM entity. So before you accelerate it, it's the dominating part, but after that, it's only a fraction. Which means if you continue to build like record-breaking MSM entity implementation, that's just a game. It's nothing useful for end-to-end performance. And this is not only a special case or corner case, like you can also see it on other things. For example, EVM circuit, which is widely used in Layer 2 project. And you also see this. So MSM entity 3%. GPT-2, like ZKPs2, funny. And the result looks better because like MSM entity still contributed to 20%, but like you can imagine, in general, this one is already the one with like, because like GPT is a kind of matrix vector multiplication, so the stuff is like the proof generation, the witness generation part is kind of easier compared to you do the commitment. So that's why it's very high, for example, 20%. But you can imagine in normal case, in normal application scenario of ZKP, you would have that portion smaller than 20%. So what you have to do is like you need to reduce the long MSM and NTT part. You need to do that part. But that part is difficult because they are coupled. They are not loosely coupled with the main thread. They are tightly coupled with the main thread. So you need to come up with better hardware architecture to do that. And then in order to do that long MSM entity part, you have to handle the diverse kernels in the long tail distribution. And if you look at the evolution of ZK algorithms, you can find that they are different in different aspects. But if you look at the lowest level of operations, you can say commitment they usually use these four, and they are used together with some kind of tightly composed like modular multiplication stuff. And so So for these 4, it's fixed. So you can write hard code hardware to accelerate it. For those outside of these 4, you need to kind of software support. And currently our plan is to use ISA for this part. So if you skip the yellow part, it is pretty common compared to a common like CPU or GPU ISA, where the only difference is you have native support to modular operations. For example, modular multiplication and modular additions. But on top of that, you have kind of hard-coded unit, for example, EC group, add, and addition. You have programmable register buffer. And these two together make it like a system that's strong enough, but also flexible enough. So comparing to the traditional CPU or CPU ISA, what is the main thing that like it can do, but traditional CPU cannot do? That is like you can easily offload very fine-grained operation to your hardware, especially hardware accelerated, hard-coded hardware unit. On CPU, if you want to offload some operations from your software, you have to go through a very complicated system stack. You have to have a system call. You go to the driver sends the command through the PCIe, and the PCIe goes send the data to accelerator card, wait for the result to be ready, and then give us like interrupt, and your system takes the data back. And that force your offloading to be restricted to those like huge operations that each of them takes like, for example, 1 GB or like at least several tens of megabytes operation, but this one can be much more finer-grained. And using this way, you can handle both those like fixed kernels, but also flexible kernels. And then we hope that like this system can support all of these kind of mainstream like zero logic proof systems. And with that ASIC design, we are going to build up with each of those ASIC die available. We are going to build a cluster on top of it, and we plan to leave the possibility to let it connect with FPGA card. So if we are lucky enough, we can do everything with our ASIC design. Then we just connect our ASIC die together to form a like unified solution. Otherwise, if you are so unlucky that like, for example, a new protocol comes out with some kind of a tricky operations that we have never seen before, and nobody expected that, how can we do that? Like we still have the possibility to connect it to the FPGA card. So even if we have some like corner case operations that like, we cannot cover, we can do it on FPGA. And we expect the card to be ready in next year. And finally, there are just 2 QR code. So on the left one, I want to remind that tomorrow we have kind of a Z prize. And actually, the track one is like we architected a competition is about end-to-end performance acceleration. So welcome to join that part. And thank you.
I guess we're open for questions.
It's too hard.
It's a bit hard. I probably have one question. So you mentioned that we can achieve some kind of linear scaling by putting several machines on the side and then getting them together into a cluster. I was wondering if there are any limits beyond which there will be diminishing returns on composing machines.
Yeah, composing machine, like every time you increase the scale of your system, like there are 2 parts that might limit your speed up. The first is like the interconnect might be a problem. For example, if you are 2 components connected on the die, the bandwidth is huge. On the same board, it's still good. If it's connected via the PCIe on the same like motherboard, the connection is restricted to the PCI bandwidth, which is pretty low, I'm sure. Like for example, PCIe 4 or 5, you have like 30 to 60 gigabytes per second. And compared to your computation power, this number is pretty small. And if you have 2 machines or 2 machines, and you have to connect it using like internet, then like that transmission time might be even longer than the computation time on a single machine. So that will be the huge problem. The second problem is if you scale, you still have to handle those sequential part, and with the speed up of like MSMT bigger, because like sequential part is like just becoming big, like huge, and sometimes like we cannot expect every part of the computation to be like parallelized. So they will always there. So you have to think of some other way to speed up it, other than just like duplicate your machine. Yeah.